Hello and welcome. My name is Alexander Lydiak, and today I'm going to talk about the work my advisor Jeshuan Gong and I uh, recently have done using diffusion maps to learn quantum phase transitions in an unsupervised way. So this work can be found below at this archive number in more detail. There's a paper, and we're trying to publish it um, in PRL as well. So we've done this work at the Colorado School of Mines in the physics department. Um, First off, we'll talk about the motivation. So we are currently in the NISQ era of quantum simulators. And what that means is we're in the noisy intermediate scale quantum. So quantum implies that the measurement outcomes are exponentially growing in the Hilbert space and exponentially grow with the system size. So in the future, when I talk about measurement samples or sample data, um, I'm talking about classical bit strings that are essentially just the measurement outcomes of essentially measuring the state of a quantum simulator in a particular basis. So these results in the intermediate scale and the quantum aspect result in huge state spaces, and these are very difficult to extract the physics of sometimes, especially when there's no a priori understanding, or the models are not simple enough to do this. This is where unsupervised machine learning comes in. So the reason it's very useful for this is because it automatically can extract features from large data sets, and that's essentially what it is state of the art at. Not only that, dimensionality reduction can help assist in theoretical understanding because you can reduce the complexity of these very large state spaces and essentially boil them down into lower dimensional representations that you can further study and hopefully understand better than the large and complex data state spaces, data sets in this large state spaces. Not only that, they are often robust to noise and can detect outliers. In particular, we'll focus on the bottom two though, feature extraction and dimensionality reduction. So first, let's talk about linear dimensionality reduction in one commonly used method, principal component analysis, or PCA. Essentially, it's this solving this eigenvalue equation. It's the eigenvalue equation of the covariance of the data. Here, X is the data set, and it's just sets of these classical bit strings at different parameter values. So you organize these in descending eigenvalues and eigenvectors. And here is just an example. So here your blue dots would be data sets or data points. And your lines here are the first and second highest eigenvalues. So essentially what the principal component analysis does is it finds the directions of highest data variance. And these are the principal components, and you can project the data onto these eigenvalues to try to retain as much of the variance and information as possible for a linear transformation. So for example, this is a 2D antiferromagnetic transverse field Ising model order parameter that is learned by PCA. And it's just the staggered magnetization. So blue and yellow are just opposite signs. So essentially it finds for this square lattice the staggered magnetization, which is of course the correct order parameter for the transverse field Ising model when it's antiferromagnetic. So it learns this order parameter if and only if it's a linear combination of the measurement samples. So for more complicated models than the transverse field Ising model, in particular, very complex systems in complex quantum matter that we don't understand a priori, it's often difficult for order parameters to be linear in the measurement samples. So examples of states in complex matter that are difficult to use linear order parameters on are topological, valence bond states, many body localized states, and other such models. So we'll talk about nonlinear dimensionality reduction. In particular, we found that diffusion maps can be very versatile and useful. So the diffusion map is diffusion in sample space. So for example, if you have this data set here, you can do a lower dimensional parameterization onto this circle. And as you can see, this is a nonlinear dimensionality reduction. So it uses a nonlinear manifold to project onto. So to go into more detail on the diffusion process, you first define a transition probability that depends on a particular kernel. And here, this kernel just depends on the Euclidean distance squared, and it is a Gaussian kernel. And here, epsilon is a Gaussian envelope size, and L is your system size. So the leading eigenvalues and eigenvectors of this transition probability define the clusters of your measurement sample sets in your state space. And it reveals their connectivity and geometric features, essentially the underlying Riemannian manifold of the data set. And you can define these leading eigenvalues and essentially the number of clusters you will focus on by defining a tolerance delta, and by tuning this delta and the Gaussian parameter epsilon, you can define the cluster sizes and essentially the features and physical features that the algorithm is sensitive to. So just to give a conceptual, an underlying conceptualization of the features that are extracted at different regimes of epsilon and delta. So here we have, look over at the bottom right, we have epsilon is approximately equal to the number of spin flips that are different, or essentially the number of measurements of in a certain axis that differ from each other. So that's represented here by R over the number of qubits or lattice sites that you have times the ln of your tolerance to the -1. So essentially, this relationship tells you what regime of what value of epsilon for a given tolerance you need to have to be sensitive to the number of spin flips or differences R. So when you have only one difference, so this is the very, very left, when you only have essentially one difference, then you just find the number of unique samples. And I'm sorry, for consistency, I should have used L instead of N here. But essentially when you only have one, you're privy to any single difference of spin or measurement, then you have just your number of unique samples as reflected by the diffusion map. Then an intermediate values, essentially between any single one and essentially half of them, which is, this is the average distance, the middle line, then you get very different behavior for different phases. And we explore this in more detail in our paper for particular models. And in particular, you can extract different phases, or you can tell that there are different phases in this intermediate epsilon regime, and they very much separate often. And for an even larger value of epsilon, you can also often get the exact discrete symmetry group order, which is quite an interesting feature. And this is essentially because these states are maximally separated. So at the top here, you can see kind of a qualitative representation of how this works. So you can think of these little blue circles as the Gaussian envelope, and whenever they are connected by overlap, you essentially have sets of clusters. So this is essentially also how a DB scan works, and this isn't exactly how the diffusion map works, but it's essentially a heuristic representation. And in general, each region is focusing on different features or extracts different features from the measurement data, and combining the full range of epsilon and exploring the epsilon dependence can elucidate different phases and phase transitions. So first we'll talk about essentially the simplest phase transition. So we'll talk about the Z3 chiral clock model. The Hamiltonian is listed here, and the parameters we tune are F and theta, as highlighted by the red boxes. This is a Z3 symmetric version or generalization of the Z2 transverse field Ising model. So originally the entanglement entropy is the best way for acquiring the phase diagram. So here you can see we have a paramagnetic indicated by PM, a ferromagnetic by FM, and incommensurate designated by IC, 3 different phases occurring here. So when you use entanglement entropy, you get this full phase diagram, but entanglement entropy is very difficult to obtain experimentally. But when you use the diffusion map on just sample data, you also elucidate the full phase diagram, and you actually elucidate it or generate it far cleaner. And interestingly, in this FM phase, it's not shown here, but the very bottom value of the color bar here is actually 3. So it also elucidates the Z3 symmetric phase, and that's the FM phase is Z3 symmetric. It has a degeneracy of 3. And it attains this full phase diagram with just sample data, unlike the entanglement entropy, which is much more difficult to generate experimentally. And that was the number of clusters at intermediate M, or intermediate epsilon. So at higher epsilon, the diffusion map method using just sample data and looking at the number of clusters will actually elucidate your discrete symmetry. And here it shows the Z3 symmetry, and we've confirmed this also with the transverse field Ising model. It's 2, and then for a higher N generalizations, Zn generalizations of this model, it also highlights a N symmetry, Zn symmetry. So it also essentially tells you or indicates that there's this symmetry present, and you can use other methods such as a Kramer statistic or a KS test to figure out exactly what kind of symmetry you have, which is quite cool. So another model that we explored, it's a little bit more complicated of a phase transition, is the J1, J2 model. So this is a dimer model. It undergoes a valence bond-like transition, or a valence bond state solid transition. And here what we show, here we show the number of clusters and its dependence on epsilon. So this is the number of clusters that you get from the diffusion map method. And essentially you feed in the samples, and we generate these samples using exact diagonalization. So it's a classical, a big, large data set of classical bit strings at different values of J2. Here J1 is set to 1. And we feed this into the algorithm, and we tune epsilon. And epsilon can be tuned after. It's essentially a very parallelizable post-processing. So you wouldn't need to resimulate the data or redo the experiment if you're an experimentalist. So here you can see the number of clusters versus epsilon. And the behavior is very different for the J2 equals 0.5 point, even compared to the 0.51 or 0.59. And to elucidate this point even more, so sorry that that line should actually be at 0.02, so it's shifted over a little bit. But you can see essentially the difference here, even for J2 very near 0.5, you have very different behavior in terms of the number of clusters. So this is just a single slice at 0.02, epsilon equals 0.02. And here we actually highlight very strongly the symmetry breaking point at 0.5. So at 0.5, this model is exactly degenerate between the even and odd dimer states. Essentially, these are singlet dimers. And the model, even though we're using exact diagonalization with the Langsat's algorithm, it will still choose one of these two states to occupy. So it's not perfect. And it's not an even superposition. So it actually detects, the diffusion map automatically detected this essentially symmetry breaking occurrence. So this like cat state breaking. And it detects it very strongly. So in experiment, there's also going to be some noise and some symmetry breaking. So this is something that could be used to detect when symmetry breaking occurs using just experimentally generatable measurement data and essentially classical bit strings. And not only that, it seems to indicate, so there's a drop there around 0.3 that might also indicate the valence bond solid transition. And it becomes sharper as you increase your system size, which is indicative of a thermodynamic limit phase transition. So we also explore the diffusion map on many-body localization phase transitions. So here is a heuristic or paradigmatic model first introduced by Hughes. Here we explore again, the number of clusters in respect to epsilon dependence. So here you can see a very different behavior for the very dark blue compared to essentially all of the other values of H. So H here is a random field that is added in the Z direction to essentially the Heisenberg model. And we've also done this with another model and found similar features. So here, taking the blue and the red slices and looking at them in more detail. For the blue slice, this represents your number of unique samples. So at low H, you can see that it very quickly dips around 2.5 and shows that the system indeed becomes more and more localized. So the unique number of samples quickly drops. And this is actually more, it's indicative of the MBL phase transition because your samples become localized as disorder increases. So they become localized around your initial state. And here I should also mention, essentially this number of clusters is generated from the time evolution of a Neal order state, and its time evolved by this Hamiltonian. So this is something that is fairly amenable to experimental realization. So you can essentially create these Neal ordered states, you can prepare them experimentally, and then let them evolve by some Hamiltonian, and then you can measure the long time evolution of these states, and that classical measurement bit string you get out of that final simulation is essentially what we feed into the diffusion map algorithm to generate these number of clusters. So if you also see here in the red curve, you can see, so this is at an intermediate epsilon, that the number of clusters actually peaks near the predicted phase transition. And this is essentially the competition, or we believe this to be the competition between the ergodicity. So the phase transition occurs around 3, as predicted by Hughes, h equals 3. And we believe this to be the competition between ergodicity and the increasing disorder with h. So you can imagine essentially you have these little mini clusters because the ergodicity lets you explore the sample space some, but the increased disorder essentially sometimes localizes you around certain points in your time evolution. So from your initial state. So there's a competition between being able to explore the whole space and being localized. And the diffusion map picks up on these essentially little mini clusters that form when there's a competing order of ergodicity and disorder. And we also find this to be the case with a different model that we explored that undergoes many-body localization, and we believe that this could be very generalizable as well. So, and we've only explored these 2 models really, so that's also a pretty cool result. And so for more details, please see our paper on arXiv. And in conclusion, these diffusion maps are a very versatile unsupervised nonlinear machine learning tool that are capable of detecting topological, so that was shown in the citation below, and discrete valence bond and many-body localized phases, as well as their phase transitions, and can even detect essentially the discrete symmetry present in your system. And it elucidates, just going back again to that takeaway and that overview, it elucidates many different features, physical features in your data set. And at different epsilon, this is a very parallelizable. So once you have the data set, you can easily change epsilon and just rerun and post-process the data. So that is another good feature about these diffusion maps. And essentially, the hope is to be able to help accelerate and understand the physics of complex quantum simulators and quantum systems using unsupervised machine learning. And nonlinear machine learning is particularly helpful because it can help us understand. It's more general in that it can be linear and nonlinear, and it can help elucidate physics and features of the system and reduce the dimension such that it's easier to understand. So this is a very useful tool that we hope to share with not only theorists, but also experimentalists. Thank you very much for listening. I'd like to thank these individuals, and thank you.